Hello everyone. Today we will be explaining you a very important product safety tool used in engineering, that is FMEA, and more specifically DFMEA. So what exactly is FMEA? Well, it stands for Failure Modes Effect Analysis, which is a structured method used to identify potential failures, evaluate the impact of those failures, and prevent those failures before it even reaches the customer. In simple words, FMEA is what could possibly go wrong and how can we avoid it. Well, there are different types of FMEA, and one of them is the DFMEA, which is the design FMEA. So it focuses on the failures that can arise because of the design issues. It is done at a very early stage, during the design stage, to make sure that the product is safe, reliable, and meets the customer expectations. And we are talking about the critical safety systems like airbags. DFMEA becomes a life-saving tool because even a tiny design flaw in an airbag can lead to major injuries during the crash. So now let's understand the 7-step DFMEA approach that we have shown in our poster. So step 1 is planning and scope. In this step, we define the objectives, set the boundaries, set the goals, who are the team members that will be involved, and all the data that is required for analyzing the airbag design. The second one is the structure analysis. Here, we break the airbag system into subsystems like sensor, inflator, cushion, and wiring to understand how they relate. The step 3 is functional analysis, where we identify what each part must do and detect the impact, like trigger inflation, maintain pressure, etc. Then step 4 being the failure analysis. So here we list all the types of failure like no deployment or late deployment or leakage or false trigger, etc. Then the fifth step is the risk analysis, wherein which for each of these failures that we have listed above, we check what is the severity, what is the likelihood of occurrence, and what will be the difficulty on detection. And through that we calculate the RPN, which is the risk priority number. The next step, the sixth step, is optimization. We implement the design improvements. It could be anything like stronger materials, better sensors, backup system, etc. Then the last and the final step being documentation and handover. Record all the changes, validations, and results, and transfer the updated design to the next team for further development.
Let's look at the product development flow for an airbag system. It starts with the concept and system definition. This is where the team decides the purpose of the airbag, its performance targets, and the safety standards it must meet. Next is system architecture and component design. Here, engineers break the entire airbag system into parts like sensors, the ECU, inflators, wiring harness, and the airbag modules. They define how each component will interact during the crash. Then we move to detailed design and simulation. In this stage, every component is designed in depth and virtual simulations are run to test deployment timing, sensor accuracy, and potential failure points. This helps catch issues before building anything physical. After that comes prototype building and DV/VPV testing. DV testing means design verification and PV means product validation. This phase includes real crash test, environment testing, vibration testing, and electrical test, and timings to check and to make sure that the airbag works reliably in every scenario. Finally, we reach the launch preparation, where the design is finalized, manufacturing processes are set, quality controls are added, and the product becomes ready for mass productions. Throughout this entire journey, DFMEA runs continuously. It keeps identifying potential failure modules early and forces them to improve the design before any major problem occurs at the customer's end. Real industry examples make this very clear. Takata's airbag failed because of unstable propellant and weak canister welds. Similarly, Mercedes-Benz used DFMEA to improve multi-stage inflators, firing circuits, occupant weight sensing, and wiring reliability. And also Tesla applied DFMEA in their Model S and Model 3 to solve issues like software timing errors, electrical noise, and signal integrity problems, leading to safer and more consistent airbag deployment.
DFMEA plays a preventive and safety driven role in airbag design. Instead of waiting for issues to appear during testing or worse, in the field, DFMEA helps engineers predict failures before they even happen. It pushes the team to think about worst case hazards like late deployment, no deployment, or accidental firing, and address them as early as possible in the design phase. It also helps them spot missing redundancies, unsafe sensor positions, and single point failures that could put passengers at risk. Every key function, from detecting a crash to triggering the airbag, is examined for how it might fail and what the safety impact would be. This leads to stronger design controls and better protection against real world failure mechanisms. By linking the highest risk issues to focused testing, DFMEA ensures that the product we launch is more reliable, safer, and far less likely to face recalls. That is what the real motto and real objective of every company who designs or every engineer who designs airbags has to go through. This is how DFMEA plays a role in prevention of failures. In short, DFMEA protects the passenger long before the car even hits the road.
Think of DFMEA as the early morning radar of airbag design. Before a single car hits the road, DFMEA exposes real risk, cutting 40 to 70% of fewer last minute design changes and 25 to 45% of failed prototype tests. And history shows why this matters. Take the Takata recall. Airbag inflators exploding because humidity degraded the propellant. A strong DFMEA would have exposed this failure mode early, long before it became one of the largest recalls in the automotive history. And on the right side, you see the payoff. Up to 80 to 90% fewer field issues and sensing accuracy increasing up to 98 to 99.5%. This shows the difference between a life saving deployment and a catastrophic miss. Real world examples also prove it. Mercedes Benz once struggled on deploying airbags on rough roads. DFME helped redesign their sensing logic and eliminate this failure. And also, Toyota once faced critical issue of airbags not deploying on angled collision. Used DFMEA-driven crash pulse analysis to redesign threshold and expand their algorithms recognition range, thus improving their deployment consistency. In short, DFMEA transforms airbags from hoping they work to knowing they work. It eliminates critical failure modes, prevents recalls, and makes every deployment safer, smarter, and faster for the passenger.